Hi everyone, welcome to Math Spellbook. I'm your host Peter, and basically we're going to re-engage with some differential equations and maybe some other maths along the way. So hopefully you guys are having a great week so far. It is Wednesday. Forewarning, I'm kind of like expecting a phone call, but at the same time, I don't know if they're gonna contact me today. So if I end up like getting a call, I will warn you guys ahead of time, just in case if I have to step away from the screen and like put the BRB screen up. Just a forewarning, just in case. But then again, I don't know if the call is gonna come today or tomorrow, or maybe they won't call me back at all. So who knows? So let's get started. So last time we were on these the Grunge-Euler, hopefully I'm pronouncing it. Is this Euler or Euler? I think this is Euler, I think. Because every time when I like stream, like I would read it, but then I would say it wrong, and like the last thing I want to do is that. So I think like I did learn this off stream a little bit, and I think I did the problems before, like off stream, but I feel as if I probably should just retest my knowledge on it. So that way I can just basically like exercise my brain to remember the info I got. So we have 2x squared. Minus 3y equals, I think they're both equal 0. So what I learned is that y is supposed to equal supposed to be equal to x or something, and then y prime is supposed to be M. And then it's supposed to be M. Something like that. I don't remember. I don't think that's the right way to write it, but I remember this part a little bit because I think you're supposed to. Because I believe it's supposed to be written like this. That with this. That should be negative M. Case is equal to -1. I think, given that it's supposed to be that y is equal to C1 and C2. I think that's the answer. Hey, what's up, Zach? If you guys are not familiar with Zach, and also I saw in the action feed you basically gave me a shout out yesterday. Hopefully the system is not deceiving me, but if you guys are not familiar with Zach, I will give him a shout out. If you guys are not familiar with Zach's work, he basically streams math as well. And he also answers some questions revolving around things related to math. So I remember the last stream I saw of his, he was talking about like some physics concepts involving math. So if you guys want to check out Zach's content for the math, and plus he's on his way to being a pro mathematician. So if you want an expert, talk to Zach. What's the best part of your day so far, Zach? So we're doing today, well, I'm doing two problems of this. Is it, I don't know if I'm pronouncing it right, grungy Euler equations? I don't know if I'm pronouncing that right. Yeah, but we're doing those today. Yeah, I asked what's the best part of your day so far. I just saw the Sevi bot. No, I was just basically saying, if you guys haven't followed Zach, be sure to check out his content. In addition to what's the best part of your day so far. Yeah, so we're doing grungy Euler equations. I believe that's how you pronounce it, because I don't want to say the wrong name, because I remember there were times when I mix up Euler and Euler. So I believe that is the correct answer. Because I think like the way it's supposed to be structured, you have to think of it as sort of like you're turning this into a simple quadratic, and you're just basically trying to solve for the m's. So move this over here. Then we'll do number 2. Number 2 is it plus? Yeah. Plus 2y prime. And then x squared. So in this case, we're given m then plus 2m minus 6 then minus 1 plus 2m we're still not done yet. Then that's plus m minus 6, meaning that we're going to have m, so 3 minus 2 equals, and then m is equal to positive 2, and m is equal to negative 3. Just put this down here, and in general y should be equal to c1 e 2x plus c2 e negative 3x. I believe that's the technique you're supposed to employ. I think they only have one answer here. Yep, it looks like... Oh, no. Oh, it's supposed to be x, not... Oh. Which means I haven't fully... I thought it was something else, dang. I made a mistake. It's supposed to be x, not... Well, at least now now it's solidified in my head now. So I have to remember that when I solve these problems, it's supposed to be x, not e to the x. Yeah, I make mistakes on stream too, guys. If you're watching this on YouTube, that's the thing. Because sometimes I don't remember things very well. I think I'm mixing it up with the last section we did, which was this section. Because they're both like order 2 linear equations, and they kind of both use the same techniques. Because you're kind of trying to break it up into like sort of like quadratics. I forgot to put the starry timer on. Okay, so for this particular scenario, I have to remember that it is using x's, not e to the x. Okay. Well, lesson learned. Alright, so let's see, functions and operators. Let's see, throughout this book we refer to a function as either f or f of x, although strictly speaking the latter denotes the value of f at x. To avoid complicated notation, we also write f of x is equal to c to designate a function f that takes the same value c constant pointed at all points x in its domain. Okay. Let's see, x. Actually, I don't know how you read this fancy one though, because I don't know if it's supposed to be a Greek letter. Now I'm thinking it probably might be a Greek letter, but then I'm probably mistaken. Let's see, x in the space of be a space of functions. Let L be an operator acting on the functions x. X works. Let L be an operator acting on the function. Oh, thank you for the follow. Immigrant Canadian. Yeah. I don't know if I'm pronouncing your name right. Immigrant Canadian. Canadian. That's a really interesting name. Hey Sasha, how's it going? What's the best part of your day so far? And also, like, is it okay if I call you immigrant? But thank you for the follow, I really appreciate it. And if you're in the chat, like, what's the best part of your day so far? It's good? Okay, cool. Yeah, we're still continuing on. Yeah, unfortunately I made a mistake here because I thought it was like e to the x power, but it's actually x. Because like before, last section we were doing, not last stream, but like before you got on, Sasha, we were doing Euler equations, I think that's how you pronounce it. And I mistakenly used e to the x power instead of just x. So I have to keep in mind of that. Oh, hello, Mathudux Puant. I apologize if I slandered your name. Like, if it is okay if I call you Mathudux. There's some fun theoretical exercise with minimal knowledge. Let E be a linear ordinary differential equation of order n, working in C to R and C with T periodic coefficients. Prove there exists a solution which is T periodic. Huh. That's an interesting one. I don't know if I have the fortitude to be able to solve that. So let E be a linear ordinary differential equation. I'm probably going to be thinking about that. Let's see, where were we? Oh yeah. So let X be a space of functions. Let L be an operator acting on the functions in X according to some rule. The linear operator is called linear if L is acting on the sum of these for any function f1 and f2 in X and any number c1 and c2. Otherwise, L is called nonlinear. But actually, Mathedux, what's the best part of your day so far, since you're chatting with us for the first time? and also providing us with an interesting math problem. So let's see, the operators of differentiation and definite integration acting on suitable functions of one independent variable are linear since, okay. Okay, so if you integrate it, then basically you receive. Okay. Let's see. Let example alpha, beta, and gamma given functions. My username means stinky mathematician in French, by the way. Oh, okay. Okay. Yeah, I apologize if I mispronounce it, because it's kind of funny, because I always wanted to learn French, but like every time when I tried to learn it, like in school, like there was kind of like a force that was like, when I mean force, I mean like there would be administrators that tell me like, oh no, like pick this up. Because I remember when I was trying to, I think in high school, I learned Spanish because I thought it was a little bit much more more common in the US. That's why I learned Spanish in high school. But then when I was in community college, I thought I was going to pick French as like a language I needed to transfer to a university. But my advisor told me that, oh, I see you have experience in Spanish. Why don't you take Italian? And I'm like, okay. And I ended up listening to him, and I basically took Italian. I don't remember any of it, by the way. Neither Spanish. I don't remember it anyway. Oh, hello, Masen. Masen69. Sure. I mean, like, if you, what's your question? And also, what's the best part of your day so far? We're actually getting a couple of new people here. I'm very thankful for that. It ain't really really much to math. Oh, okay. Okay. Sure, what's the question? And if you guys are new to the chat, welcome. If you're lurking, it's okay to lurk, but if you like math, physics, or just need a productive stream to keep you preoccupied, you know, drop me a follow on Twitch if you like. In addition, if you're watching this on YouTube, because I upload my VODs on YouTube, you know, the typical, hit a like, comment, and subscribe. Don't be slowing down rigorous words in your course. Read diagonally. It is enough for most sentences. I don't get what you mean. I mean, I'm not taking a course. I'm just basically just learning. I'm just learning. Math is like a hobby of mine. So where were we? Oh yeah, so alpha, beta, and gamma be given functions in view of preceding example. And for all those that are new, like if you guys like see me reading or something like that, you can still put stuff in the chat and I'll read it. I usually, when I think of these, like even though they're considered study sessions, I just basically think of it as like, oh, I'm working on a problem and you guys are just like a desk near me. It's like, hey, I have this like I'm doing research on this particular thing. Do you mind like hearing me out? And I'll be like, yeah, sure, share your idea. And when you share the idea, sometimes like you'll be thinking about the idea, and when you're sharing it, you're like, wait, I didn't think about this angle before. And then you started like, oh, I gotta get back to my work. Think of it that way. That's how I think of the study sessions here on stream. It's just basically just us, like we're like our own little research team, just basically researching our own little things. LF is equal to alpha F prime and beta F, oh no, F double prime, and then beta F prime plus gamma F is linear. Okay. Let L be an operator defined for all continuously differentiable functions on R by L times F and F. So, okay, since the particular choice of C1 is 1 and C2 is -2, f of x is equal to x and f2x is 1 yields, okay, -1x, okay, which is equal to x and not equal to. So include that L is nonlinear. Okay, so this one is a little bit more abstract. I have not handled proofs yet, so let's see. A differential. This probably doesn't have anything to do with proofs, but at the same time, I'm like, wow, this is like getting into like more of the abstract stuff. A differential. Oh, by the way, Monsen, what's your question? Because you said you had a question. Oh, we're probably in an ad. Oh, I didn't see that. Oops. If you had to play split or steal against 20 people, and okay, against 20 people, each two faced each other for a game of 200 rounds, and you are all playing based on strategy, no mind games, involved almost like playing online without talking. Each round is both steal, they both steal, they both get 1 point. If both split, they both get 3 points. Is one steal, one steals and one steals, he gets 5 points. So what sequence would you think would be the best to gain the most points in the face-off? Interesting. So you either split or steal against 20 people. So each group is made up of just 2 people, and you have to play 200 rounds. Damn. So you both have, so both Mossen and Mathodux has given us a question. So let's just write down Mathodux's question so I don't forget, actually. So I'll just write it down so that way I don't forget it, because I know when chat starts moving I'm going to like miss it. So let E be linear ODE of order n working in C. I'm guessing this is supposed to be the real numbers and the complex numbers, with T periodic coefficients. Prove there exists a solution which is T I meant if one steals and one splits, the one that stole gets 5 and the splitter gets 0. Okay. So let's move this over here on the side. So 20 people, 2 per group, and 200 rounds. And the rules are so I will write conditions, or maybe you should just write game conditions, like Squid Games. Okay, so both steal. They both steal. They get 1 point. If both split, they get 3 points. And if one steals and one so I'm guessing this is the one. So if one steals and one splits, that equals stole 5 points, splitter 0 points. Okay. Like, you can have a sequence always mimicking his last pick. However, that can make you get less points. So how can you use a sequence that you can make you get the most points out of each round? Huh. Okay. So we're given like 2 problems here. So first of all, I have to know what is T periodic. I have to figure out what that definition means. Let me see if I can look it up and see what it means. Let's see what it says. A function f. At least Google AI gives us a straightforward definition. Well, I wouldn't say straightforward, but at least the AI gives us a definition. Okay, a function f is t periodic. Just underline that. If there's a positive number period such that for x, for all of x, oops, for all x in the function's domain, ft plus x is equal to and also let's see, in other words, the function's value repeats itself exactly after an interval of t length, of length t. Ooh. So it doesn't matter what you put into the function, what you add to it, you basically will get the same result, f of x. Let's see what else they have here. Let's see. Period t, the function, the positive value of t that satisfies t periodic properties is called the period of the function. Repeating pattern. Oh, they show an example here. Let's see. Sine function. If I'm interrupting the math and making others have to wait, I'm sorry. It's okay. It's okay if you don't. No, it's okay. It's okay. I mean, like, do you need the answer to the problem right away? Because, like, I just basically solve math for fun. I'm not really a person that basically takes on random questions that much. I mean, like, if you're on a time block, I basically just study math on my own. So you're good there, Masen. Actually, like, tell me a little bit about yourself, actually. And actually, anyone that's new, like, you know, like, where are you guys from? Like, are you guys graduate students, or are you guys just undergrads? Are you guys in high school? What brought you guys into math? Or physics? Or both? I'm actually glad you guys are presenting problems because it gets my brain thinking about different ways of thinking, I think. Although I'm not an expert, so I don't remember stuff like from like calculus 2 or anything like that. I just basically do math as a hobby to basically like learn more, mainly. So there's no need to feel like you're interrupting or like you're like, I'm just glad you actually put the questions up. So they use sine of x and then is 2 pi periodic because sine is equal to, oh, okay. So let E be a linear ordinary differential equation of order n. So in other words, for some reason I keep thinking of like something like really, really absurd. I'm in high school, a junior. I actually enjoy math and physics really very much. I'm guessing that you mean very much. However, it's quite easy in school. It feels like I'm not really solving math, if you get what I mean. Yeah, I think so. You feel like it's spoon-feeding you. Oh, you're from Egypt. Okay. That might sound weird, but yeah. Oh, okay. Gotcha. I see. Well, at least you're like, you know, like you're passionate about it. So, you know, like I said, I'm probably like around your level. I'm because I only took like calculus 1 and I barely remember calculus 2. I know some concepts from Calculus 3 and some from differential equations. So I'm basically trying to like work my way up to like learn higher maths for physics, as well as learn some physics so I can understand like the equations within the maths as well. So hopefully your studies are going pretty well for yourself, Masen. And if I'm mispronouncing your name, please let me know. Yeah, but if you love math and physics, like, you know, consider following my channel if you enjoy watching me like solve problems, or, you know, just talking to you guys. Either way. Oh, thank you. And you're the 70th follower. Thank you. Lucky 70. we met a goal of 70 followers. Nice. I'm still taking matrices. Oh, okay, I see. Hopefully you get there one day and become a... No, I don't think I could become a physicist. It's kind of funny because I did take I think I took like a career quiz, like online. It wasn't official or anything, and it's funny. Oh no, I think it was the Ikigai test. If you guys don't know what Ikigai is like a Japanese philosophy where it's like it's like a job that combines everything, like your passions, what you would like to make money off of, what you're good at, and what you're passionate about, and it's basically your life purpose. And it's funny because like when I took that quiz, the result was physicist, and I was like, I don't think so, because I don't see myself going back to school anytime soon. I like learning math and physics as a hobby. I don't think I have the tenacity to do a PhD or anything. Let's see. So it's 20 people, 2 per group. Let's see here. And you have to play 200 rounds. When you think about it, that's actually pretty interesting. Because... let's see, both steal get 1 point, both split give 3 points. So 1 steals and 1 splits. So the splitter gets 0 points and... Actually, this is a very interesting one. Yeah, the S represents scenario, so... So let's say if player 1 steals... Like, let's say they steal, like, all 200 games. and that means they would get, and then if player 2 would get 0, and if player 2 steals more, then they would get 1,000. So this is kind of like a game theory type of question. So the thing is, oops, I probably should move it a little bit for you guys because you can't see the other side. There you go. Sorry about that, guys. And this is basically based on if, like, you know, player 1 basically steals and player 2 splits, and, you know, player 1 splits and player 2 splits. But of course, like, if it's this type of scenario, then one player would actually gain the intuition of the other, and basically they would probably just both steal at this point. So in this type of scenario, no one trusts one another. If they both split, then they both get 300, which means, like, I mean, they both will get 3 points each. And if they're playing 200 games, then basically they'll both end up with 600. This, so scenario 3, where it's like one splits and one steals, I feel like eventually a player will basically get the idea of what the other player's doing. So then they will say steal, and then each player will get 1 point. So I think the best scenario, at least, like, I'm thinking, like, you know, like how it would be for game theory, because usually when you do game theory, it's like I'm not an expert on game theory or anything, but I remember, like, watching movies about certain game theory type problems, and it seems like this would probably oops, I thought I had my pen available. It seems like this scenario seems like you can get the most points, because either someone is going to split, or when they catch on that someone is stealing too much, then they'll probably try to steal, and then basically you will still get a point for stealing, and they will just get 1 point. But then, like, if someone catches your strategy, like, beforehand, so you both will either end up stealing, or one of you is going to split, and then basically, like, you will lose a point if you split. In either way, whoever steals first gets ahead. I mean, that's based on the logic I put in. I don't know if that answers your question, Masen. I could be wrong, but from the way I think about it, it seems like if you're very competitive, more people would probably try to get the, I guess, like, the most out of their strategy. And it seems like the way this game is set up, it seems like if you plan to steal, you're either going to get 5 or 1 point. So if both people decide to steal in the beginning of the game, you're probably going to end up with 1 point. But if one person decides to split and one person steals, you still gain 5 points, which means that gives you a higher advantage. I mean, that's how I think about it logically. I mean, if anyone in chat wants to say that I'm wrong, or, like, you know, put out an argument against what I'm saying, please do, because you know, I'm probably not thinking about other scenarios. But I mean, this is a legit math problem when you think about it, because you have to think about how the game works, and you have to also think about I guess you also have to think about a little bit of human psychology. So I actually enjoyed this. This actually made me think really deeply. And, you know, like, did you create this problem yourself, Masen, or you just found this in a book somewhere? I don't know if they have answers in the book that tell you, like, what is better, what's the better answer, but if logically, when I think about it, like, I say logically, but we humans are never logical, even when we think we are being logical. I think that, yeah, I think, like, basically you stealing is probably a better scenario for yourself if you're the player. Because you end up with two different types of scenarios. Either you steal and the other person splits, or you steal and both of you get points. So either way, depending upon the person you play, like if you guys keep stealing, you're just gonna end up with 200 points. Whilst if you both, if one person decides to split, then they have to hope that you split with them. If you don't, then they're gonna get 5 points and you're gonna get nothing at this point. Yeah, I did it, and my friends are trying to solve it for a prize, but I need the perfect answer, so I'm looking for it. Yeah, but at the same time, I don't know if my answer is considered quote-unquote perfect, but the way I think about it, it seems like stealing is going to give you more benefit than splitting. I mean, that's the way I see it, but, you know, like, if you really, I think, like, if you think to yourself, I think you'll probably be, you probably might come up with a different solution than me, but, like, I would say, like, test the hypothesis first, because I probably am wrong. But to me, I feel like there's more benefits to actually, like, stealing in this game than splitting, because when you split, you have to hope that the other player splits with you, and if they don't split, then you're gonna end up in a scenario where you lose points or you get 3 points. And if the player is ahead of you, they're gonna get more points if they decide to split with you, because they can choose to split with you. But if they're ahead, I guess when the other player's ahead, they can feel like, oh, I can give you some points. So, yeah. That's what I see. Now, Mathadux, I don't know if you're still in chat, but yeah, this problem looks really, really, like, abstract. Let's see, it's working in C, which is probably like a set with the complex numbers and the, okay, so we get like two different numbers here. Sorry about that, guys. I'm just like taking a drink of water. No, you're welcome. You're welcome. I mean, I don't know if it's the right answer, but at the same time, like, that's the best I can do thinking about it. I mean, hopefully that helps. Because I feel like if you're still in high school and you're thinking about games, I think, like, when you think about games, it gets you more engaged with, like, if it involves math and gets you engaged into how the scenarios work. Okay, so a function is a t periodic if there's a positive t. So what we can say, so basically this, let's say it's a function of order n, right? So I'll put fn, and it's a differential equation. The reason why I'm using L is because of this particular chapter, or this section, I should say. And probably I should put like I should probably put x in here, and that would equal well, actually what I should write is plus t equals question is, how would you prove this? Leave that in our back pocket for now. Let's read more about these things. Let's see, a differential equation of the group LU equals G, where L is a linear differential operator and G is a prescribed function, is called a linear equation. If the operator L is nonlinear, then the equation is called nonlinear. Okay. The following almost obvious result forms the basis of what is known as the principle of superposition. Okay. If LU equals G is a linear equation, and U1 and U2 are solutions of this equation with G equaling G1 and G equaling G2 respectively, then U1 plus U2 is a solution of the equation with G equaling G1 plus G2. In other words, if LU1 equals G1 and okay, so it's the sum. Proof. This follows immediately from the definition of linear operators. A linear operator. Okay. Okay, I don't want to look at the answers here. Alright, so verify the given linear ordinary differential equation is linear or non-linear. Okay. So I think we're done with this problem, but this was a pretty good problem. Thank you for sharing that with us, Masen. I'm going to erase this so I can actually have space, so I can write these other problems down. I don't want to write underneath the one that Mathodux is showing us, because I feel like we can learn a lot from that one. Maybe I should do this. Almost break time, but I'm just going to write these problems down so we know what we can continue on with the next study session. X is equal to that. Number 2, y prime plus 2x All right. got those problems written down, so when it's the next study session, we can cover those. So, thing of it is that like, I think like when it comes down to like learning like math in general, like there's got to be like something like deeper in it that you end up loving actually. Because like I said, like to you guys that have watched my streams for a while, I loved math. I was starting to love math because of physics, and then I realized that math is much bigger than physics in some ways, because it's kind of like its own little world, you know. At the same time, I think it's like, because math is so abstract, it's kind of hard for people to get into it, because they don't have any visuals or anything, and sometimes like I guess in math like visuals are kind of like an unneeded thing. Let me see here. Actually, like before I got on stream, I was actually watching this lecture by Tom Crawford, Dr. Tom Crawford. If you guys are not familiar with who that is, I think he's like a mathematician from Cambridge, I think. So maybe we can like watch it together during break. So let me just turn on the browser so you guys can hear it. I'll just mute the music for now. And we have like 12 minutes. We can probably watch 12 minutes of a lecture.
It is a real pleasure to be here, and wow, there is a lot of people in this room. This is awesome. So I'm very excited. I have given many talks over the last sort of 7 or 8 years since I've been doing this. But it's not often I get to do a brand new talk. So I don't know whether I should have told you all this, but this is a brand new talk that I haven't practiced because I wanted to do something that linked to the theme. I love the idea that we have this theme of codes running through the lecture series, and I really wanted to speak to that theme and try and
hopefully you guys can hear it. If you guys can hear it, I'll fix it.
And in particular as someone who works in mathematical modeling. So it's kind of going to be a little bit of a sort of a run through history.
I watch too many lectures, but I don't do enough problems.
And the idea being that, from my perspective at least, mathematics, equations, mathematical modeling is one way that we can try to understand the code of the universe. So the universe exists, things happen, we want to understand them as humans, and mathematical modeling gives us a tool and a way to try and do that, to try and sort of unpick that code. And that's kind of the theme that I've gone with, and that's what I'm going to talk about for the next 55 minutes or so. And I thought I would start, when my clicker works, there we go, with a sort of example of why mathematics might be a good way.
I'll definitely put a link to this lecture in the description down below for anyone who's watching on YouTube.
This is the Golden Voyager record, which was sent into space in the 1970s, which was sort of a selection of songs from around the world that were seen as a way to communicate the variety of life on Earth and sent to other potential alien life forms around the universe. And also shown on the right of the screen is the Arecibo message, which again was sent out in 1974, communicating various bits of knowledge that we have discovered as humans, including you've got the numbers at the top, atomic numbers, we've got formulas for DNA, a sort of this lovely cartoon of a human shown there. But there's sort of, to me, when I look at this, I see this idea that we, as humans, have decided that perhaps using mathematics, using equations, might be one way that we can communicate with other life in the universe. Perhaps the mathematics, the equations, the numbers are this commonality we might have with other life forms. So that's sort of my argument as to why maths and modeling might be a good way to sort of decode the universe. But then, as I was thinking about this, I then remember when I first got into communication, I was very fortunate to interview Professor Ian Stewart. Oops, I've skipped too many slides there. There we go. I was fortunate to interview Professor Ian Stewart. He's a mathematician at the University of Warwick.
I have one of
And
his
we talked
books.
about this concept of, is maths the best way
Like,
to
what is
communicate
math?
with other life forms? And I'll let you basically read what he says on the screen. But he sort of said, well, the maths that we have, the way we interpret the universe and our world, is very closely related to, our planet. So this idea that, close on the surface of the Earth, basically our planet is Euclidean. Everything is kind of like straight lines. But if you zoom out, then you begin to bring in curvature, and the Earth is no longer flat. And as he mentions here, if you are an alien life form that has grown up on a gas giant, like Jupiter, maybe talking about triangles and squares and straight edges makes no sense. You're like, I don't get that. But, possibly understanding Navier-Stokes, one of the great unsolved problems currently facing mathematicians, maybe that makes sense if you grew up on a gas giant planet. And so I just thought this, again, a potential interesting counter-argument to whether or not our maths is the right way to decode and interpret the universe. Okay, so as I mentioned, I wanted to sort of go through history, pick out various mathematical models and ways we have tried to use maths to understand our universe. And I'm going to use this brilliant resource. This is called the Timeline of Mathematics, on a website which is called Mathagon. Really fantastic free resource. And it shows various mathematicians and results throughout history. So we're going to go back to some of the first sort of bits of mathematical modeling in ancient Greece. And in particular, we're going to focus on Plato. And we're going to look at one of my favorite mathematical models. And this was Plato's attempt to understand the universe and to model the universe. And it actually starts with some shapes, which are named after Plato. And these shapes will satisfy a series of 3 rules. So in order to be considered as one of these shapes, you must first of all be a 3-dimensional shape. So these shapes are called the Platonic solids after Plato. So in order to be a Platonic solid, you must be 3-dimensional. So we want something that's not flat. We want it to have that 3rd dimension. The second rule is you want every face that's on your shape, we want to be the same particular shape. So if one of them is a square, we want all of those faces to be squares. If one of them is a triangle, we want them all to be triangles. And then the third one is a little bit more technical. We want the same number of faces to meet at each corner. So if at one corner of the shape there are 3 squares joined together, then at any other corner there must be 3 squares joining at that corner. And now with these 3 simple rules, and this is why they fascinated Plato, there are actually only 5 shapes that satisfy these 3 rules, which to me is quite amazing because they feel very general. They feel like there's a lot of variability in that. And this is, again, what fascinated Plato, the fact that you can prove, and I'll very quickly show you how you prove it in a minute, that there are only 5. So does anyone know what some of those 5 might be? Cube. Yes, the cube. OK, that's going to come up second. I need the one before the cube. OK, good, right. So the joys of having a PowerPoint slide that must go in order. So the first one is the triangle-based pyramid, or the tetrahedron. So you've got 4 triangles, 4 triangular sides. At the corner there, you can see there's 3 triangles joined, and that will be the same at every corner. So it does satisfy all of our rules, and obviously it's 3D. Then we've got the cube. Again, squares. There are going to be 6 of them in total, 3 of them joined at every corner. Next. Octahedron, yeah, very good. So we're counting up in number of faces. So the octahedron has 8 triangular faces, and at each corner, 4 of them join together. So an octahedron is basically 2 square-based pyramids stuck together. It's a way to think about it. There are 2 more? Yeah. Dodecahedron, very good. So the dodecahedron has pentagon-shaped faces, so 5 sides, and there are 12 pentagons in total, and at each corner there are 3 pentagons joined together. And then the last one. Yes. This is good. I don't think I've ever had an audience so Knowing them all in order, brilliant. Right, so the icosahedron. So this is 20 triangles, and at each corner you have 5 of those triangles joined together.
Might as well roll a d20.
And actually, interestingly, wasn't Plato that proved there were only 5 of them. It was actually a Greek mathematician called Theaetetus. So really, they should be called the Theaetetan solids, which I think is a much, well, less catchy name. But he was the one who actually showed that there were only 5. And he did it by looking at the angles. So again, I will quickly just explain how this works. So if you open them all out and look at their nets. So if you concentrate on one of these corners, so for example, I think the first one I'm going to highlight is the cube. So if you look at the total angle that's at a corner there, you've got 90 plus 90 plus 90, you've got 270 degrees. Now, if you only have 2 square faces joining, you cannot make it 3D, because you either stick them together that way or that way. So it's not 3D. So you need a minimum of 3 faces joining at a corner to make it 3D. But you can't add a 4th square, because what happens if we add a 4th square? It goes flat. There's 360-degree angle, it's flat. So you can't, and then obviously you can't put more in. So you can't actually build anything else with squares, right? Because you need at least 3 to make it 3-dimensional, but if you get to 4, they don't fit. So the only 3D solid, satisfying our rules, that you can make from squares is the cube. So then you say, okay, well, what about pentagons? Let's go up to the 5-sided shape. The angle in a pentagon is 108 degrees. So you have 324 degrees at that corner. So again, you can't fit a 4th one. And we're not allowed to have another shape because all the faces have to be the same shape. So you can't build anything else with pentagons. Hexagons. What's the angle at the corner of a hexagon? Good, 120. So if you put 3 hexagons together, you get 360. It's flat. So it doesn't work. It doesn't satisfy rule number 1 about being 3-dimensional. So we can't use hexagons. And then if you went to a 7-sided shape, you can't fit 3 of them together. It's more than 360, et cetera, et cetera. So the only one that's left is triangles. And that's why there's so many of them made of triangles. So you've got your tetrahedron, has a total angle of 180. Your octahedron is going to have a total angle of 240. You put 5 of them together to give yourself the icosahedron, which is 300. If you add number 6, it's flat again. And so that's kind of what Theaetetus did. And then Plato comes along and is like, these shapes are incredible. They're beautiful. They must have some deeper meaning in the universe. And this is where the modeling comes in. And so he says, right, these have this incredibly important meaning in the universe. And there's only 5 of them. And the universe is made of 4 elements. First little hiccup in his problem, right? But, you know, Plato is known for being quite creative. So we've got fire. We've got earth, we've got, don't know which one's going to appear next, water, and we've got air. So this should have possibly suggested this wasn't a perfect model and perfect theory. But Plato decided, well, let's create a 5th element, call it the heavens. So now the universe is made of 5 elements, and Plato's theory, his mathematical model, is each of those elements is made of small pieces, and those small pieces are one of the Platonic solids. So there's 2 ways of looking at this. First of all, you could say that's ridiculous. But also, you could say, well, it's kind of true, right? The universe is made of lots of smaller pieces. We just now would call them atoms and molecules. And they definitely do have shapes. So it's not a million miles away, 3,000 years before we sort of get to where we are now. But what I want you all to do, and this is your first interactive task of the evening, 5 shapes, 5 elements. Which shape is which element? I'll give you a minute. I actually want you.
I think we'll leave it at that. So if you guys are watching this on YouTube, you can basically watch the rest of the lecture in the link I provided in the description below if you're watching this on YouTube. For guys in Twitch, I will post the link in the chat for you guys so you guys can look at that yourself if you want to check it out. Okay, so before we continue on with our study session, I will just be right back real quick, so give me a quick second, guys. Alright guys, I'm back. So, I think we can continue on with the study session. Let me just turn our music back on. Where's my mouse? There it is. So we'll turn this back on. And we'll turn the study clock back on. And let's carry on. So, we're working with these problems. Verify whether the given is linear or non-linear. So I feel like this is just defining which one is linear and non-linear, huh? So I think one is linear, because I remember like when you first learn differential equations, you have to know which one looks linear and which one looks non-linear. So this one I think is non-linear because it has a sign with y in it. So I think that's non-linear. I'm pretty sure it is. And then for number 3, this one looks like it's non-linear because like the way it looks is that it's mixing the derivatives together. 4 looks like it is. It looks like it's a linear one because even though it has like just y double prime and it doesn't have y prime, it still has y and like by itself. So I think it's linear. All right, so let's take a look. I think it's only going to answer 1 and 3. So 1 is linear. We have linear. Okay. 3 is non-linear. Yeah, you got that right. So I'm thinking like our logic was correct in thinking that. Ooh, Fourier series. Okay, so this is going to be new for me because I've never done Fourier series, let alone I've never done Taylor series either. So hopefully they do a gentle approach to this one. Okay, so let's take a look. It is well known that infinitely differentiable function f can be expanded in a Taylor series around. Oh, maybe that could give us a hint to what Mathodux was trying to show us with his problem. So maybe we can write a little bit something in our notes. Taylor series. Maybe write a little sneaky hint right there with a smiley face. Okay. Okay. So let's see. F can be expanded in a Taylor series around the point x naught in the interval where it is defined. Excuse me. F of x. So we got the series. So we got a Taylor series there, with the coefficient Cn given by Fn x naught over n factorial. Okay. So f is okay. So it's kind of giving us a little bit of notation we can use if we're going to construct a proof for Mathodux's question that they proposed for us. It's kind of funny how it goes full circle, huh? Mathodux basically introduced the problem, and now we're reading about something that could probably help guide us into thinking about the problem. I'm not going to say it's going to give us the answer. It's just basically going to be our guide to probably think about how to think about the set problem. Maybe. Who knows? If certain conditions are satisfied, then the above series converges to f pointwise, that is, at every x in an open interval centered at x naught. And we can use the equality sign between the two sides. Okay. In this chapter, we discuss a different class of expansions which are particularly useful in the study of solving partial differential equations and can be constructed for functions with a much lower degree of smoothness. Ooh. Okay. Let's see, a full Fourier series. This expansion forms. Ooh. That looks like a real doozy. Where L is a positive number and A naught, AN, and BN are constant coefficients. Let's see definition. A function f is defined on the real numbers is called periodic. Now we're actually getting into periodic now. So maybe this section will tell us about how to solve the problem that Mathematics presented us. And we just looked over this definition. It's periodic if the number t is greater than 0 such that f of x plus t is equal to f of x for all of x in the real numbers. Okay, let's see. The smallest number t with this property is called the fundamental period, or simply the period of f. It is obvious that the periodic function also satisfies f of x plus n t is equal to f of x for any integer n for all of x in the real numbers. Let's see, so the well-known examples, yep. Okay, we see that each... Okay. Yeah, and then like, this would be equal to... It's like whatever number it's going to be, but then it's a multiple of x of 2 pi, which means it's going to be equal to like, it's going to be equal to 1 in this case. 1 or negative 1 depending, but I think it's going to be like, it's going to be a multiple of 2 pi, so it's going to be positive 1. Okay, and yeah, so this would be 0 in this case. Okay, so the right hand side of 2.2 is periodic with a period of 2L. This suggests that the following method of construction for the full Fourier series of a given function f defined on minus L, positive L, be represented by a graph. Okay, we constructed a periodic extension of the periodic L2. The value of f at x equals negative L is left out so that the extension is correctly defined as a function. For the extension f, it is now possible to seek the extension of 2.2. All we need to do is compute the coefficients a naught and a n and bn and discuss the convergence of the series. It is easy to check by direct calculation. From L to L. So in this case, L plus 1 equals 0. So it equals L when n is equal to m, and equals 0 when n is not equal to m. Oh, so there's like two different versions here. One thing I'm wondering is that why they have double cosines here. And why is there an m, cosine m pi x equals L? I mean over L. Exercises here. So this one's going to be probably a little challenging because there's a lot of text here. Hey Famish, how's it going? What's the best part of your day so far? We're just learning about Fourier series now. My first exposure to it. Sorry. I don't know why I'm like yawning a lot. And I don't think like it probably might be like me looking at the math book. Not much, just eating ramen with tuna, eggs, oh, that sounds delicious actually. You're kind of making me think about like actually, like it's been a long time since I had like macaroni and cheese. I can have ramen like probably like once a week, but at the same time it's like I haven't had like macaroni and cheese in like a long time. And I think like there was one time I was like watching YouTube and I was like I think I saw one of my favorite mukbang YouTubers. He was eating like macaroni and cheese with like different types of meat in it. Like I think he mixed like a bit of brisket with some like maybe like I think like beef steak or something, and then he chopped it up and put it with mac and cheese, and I was like, oh, that looks delicious. And then when I thought about my experiences eating mac and cheese, I realized that I have not eaten mac and cheese with like meat in it, like whether it be hot dogs or something like that. And I'm like, oh, I realized I never ate mac and cheese with meat in it. I probably should put that on my bucket list. Yeah, I tend to eat ramen with eat once or twice a week. Mac and cheese with meat, yeah. It's a combo that I actually haven't done yet, and I'm like, oh wow, I realized that all my years of eating it, I realized I have never actually mixed meat with mac and cheese. So the one thing that I'm getting confused about is, well, first off, the way this graph looks. I think that's the one thing that's kind of confusing me, because I'm like, how did they end up with that result? Or how that looked anyway. Because, let's see, if L's up here, then these will cross out, and then basically we're left with X. And then, so we get 2 L's. Well, actually we get 3 L's. Because if L is in the integral here, then it will also be X. And then basically we have like 1 times like, and then L will cross out at the bottom, leaving with pi. Yeah, so it will be 0. Oh no, wait. Yeah, because this one will be equal to basically pi in this case. Oh, no, pi. No, cosine of pi is -1. Oh, hello, breathe deeply. What's the best part of your day so far? Yeah, we're working, I'm trying to read more on Fourier series. We just hit this section just now, so... Do I know enough math to get through, to understand it? Maybe not. I might have to actually look... I might have to, like, look back and see what I have to practice first before we get into this, this branch. And I think that, I don't know if this is so if it's Fourier series, I think we're actually starting a little bit of the partial differential equations portion of this book. Maybe, I don't know. If you want to get knowledge worth a math degree, I recommend OSU? For some reason, I'm thinking of the game. I'm thinking of the video game OSU, but I know that's not what you're talking about. Click the circle. Open Source Society University. Let's see. University Path to Self-Taught Education in Computer Science. Is that what it is? They offer free knowledge in math and computer science using free resources. Oh, okay. Okay, I'll put that as I'll bookmark that so I remember it. Because if you guys actually have stuff that you know, like people in the community use, definitely I'll take a look at it. Oh, it works with GitHub. With GitHub, I never actually worked with it. I mean, I've never like downloaded stuff from GitHub because I knew it's basically a bunch of files sometimes. And sometimes, like, you know, like when I look at it, it's very intimidating because I'm like, oh, am I supposed to download this or this or that? Because I know, like, a lot of people that do computer science use GitHub a lot. And I think some mathematicians use it. Technically, it is free resources, but they give you a syllabus of sorts, which I like. Oh, okay. Let's see, curriculum. Course of conduct. Well, thank you for presenting that to me, Famish. I really appreciate it. Let's see, there's nothing on the homepage. Oh, here we go. Advanced math. Essence of linear algebra. Formal logic. Oh, that's gonna be fun. Oh, they have prerequisites. Oh, we have set theory, we have differentiation and integration. Let's see. Modern robotics. Interesting. I'll definitely keep it in mind to actually like keep a close eye on it. Now the one thing I'm not understanding is that why did they wrote this? Why is there two cosines in here? Like, what is the point they're trying to make? Is it because there's one with m in it and there's one with n in it? So it's L if n is equal to m, and it's 0 when n is not equal to m. Kind of reminds me of what do you call it? The dummy variables in I think, index notation. And I'm probably being very basic here because I'm like, why is it that this is 0? Does that, well, since it's integrating, it has to do with the area. So L to 0, but then we have to go to L. Huh. Is it because I'm like, I feel like I'm lacking knowledge from basic pre-calc? I'm like, why is it that I'm not seeing the fact that those are 0? School is expensive, so it's always nice to get the knowledge for free. Yeah, absolutely. Maybe even land a job, especially with math, anything in tech related, you can. But if you ever want to get a degree, you can get one and breeze right through it. Yeah, that's also true. Yeah. I don't think I'll ever be able to have a chance to go back to school to get a degree in mathematics or physics or both. Actually, if I were to go back, I probably would try to get both. People will probably think, "Are you nuts? Why would you do that?" And I'm like, because I love both subjects. But that is, I would probably go back if I didn't have to worry about working during school, because if I had to work during school, I'd be like, forget it. Because I tried that and it didn't work, and I was, well, the reason why I say it didn't work is because I got tired very easily, and I basically, my social life was like, it felt like it was totally like non-existent, because I had to worry about getting home, doing the homework, and then I didn't have anything else to do besides probably watch anime or something. And it felt very miserable. It felt very miserable doing that. And then at that point I just ended up dropping out, and I was like, forget it, I'm not doing it. Like, I mean, I love learning, but I can't learn and do a job at the same time. Like, I mean, pressured to learn, that's what I mean. I can't be like in a classroom when I'm pressured to also work on the next day. Like, I'm doing this practically for free, like basically just like streaming to you guys while doing math, because I feel as if this is something that I would rather enjoy doing. It's like basically learning with you guys, because you guys are just like more knowledgeable than me about these subjects, and you guys probably see stuff that I can't see yet, so it's like pretty cool. It's like pretty cool to be able to engage with you guys without having to be in an academic setting. It's like I don't have to go to a university because I have you guys, because you guys are probably doing stuff that are already involved in academia, or at least like doing something that has more application if you're working, but you're still using math. Or maybe you guys are just like hobbyists like me, and you just basically just want to learn. Yeah, it's like you said, Famish, never stop learning. Never stop learning. You might not get ahead when it comes to like I mean, it's better for you to learn like stuff so that you can probably be at least able to understand the communication involving those things, whether it be math or whether it be something like more equitable like psychology or music or finance or economics or something. Sure, you might not be like having no experience with those things, but at the same time you kind of have an idea of what exactly is being talked about, you know? So that way you can get used to like the diction of those particular branches within like certain career paths. Let's see. Yeah, this one I'm not getting. I'm like, why do they show this? Formally equality. So A is equal to 1 over L, and L is okay. So if we put this in here, incorporate. If we allow n to take the value of 0, well, so we multiply. What is 2? Okay. Which completes the construction of the full Fourier series of f. The numbers a0 and an and b given by these equations are called the Fourier coefficients. Interesting. So if you write it all out, then basically the Fourier series would look... I think we can have a little fun with it. So let me take my pen here. Let's move this to the side, because I feel like this is a problem we can get into a little bit later, and I think we can get rid of this. We can erase this. Actually, I should probably do this. Then let's get rid of that. Then sometimes I like writing like stuff that we see, so f of x, just put a line there, so a half a naught sigma to infinity n is equal to 1, and then an times cosine of pi, and x l, and plus bn sine n pi x l. Then if we go down here, so a0 is equal to, I think, 1 over L, with L going to L, f of x dx, and then an is equal to, I see you're doing linear algebra. I mean, could be, I guess. I don't know. Maybe I should probably do the textbook that has like linear algebra with differential equations, because I do have a textbook on that, like in my room. And then n is equal to 1, 2, 3. Let's see. Actually, Sascha, how's your research going so far? Because like, it's about like a month away before you actually have to present your stuff, right? Are you still working on that last chapter? Sine. Dx. And now, I think we can do some fun here. So now, let's see. Well, actually, it will be too long for you guys to see. So, I think what we can do is f of x is equivalent to, then we have to like drag this up here. Can we see all of it? Let's put it on the side here, like that. And then have some fun and act like we're doing some hardcore math here. Even though we're just recopying everything, but I think it would be very fun to do it. And plus sigma. For some reason I like it when it's written in long form, even though it's probably like ridiculously long. I mean, if someone who doesn't understand math walks in on you when you're writing this on a chalkboard, they probably thought you were like really intelligent, even though you're just recopying everything. And I don't think we can fit all of that. Let's see, plus, and then we get B. Which is then we're add that. Actually, that looks pretty. Oh no, it's not covering all of it. I hate that. Because I don't want to... Dang, I wrote it too crooked. If I wrote it straight, it would work. Oh well. I don't know why, but when I look at long equations like this, I think it looks pretty. Even though it probably looks like a freaking mess. Because like when you see it in its full form like that, I think it's like, I think it looks pretty cool. You could probably, I bet you like people that like do filming for like mathematician movies or something like that, they probably have people like write stuff like this on the blackboards to make the main characters look smarter. I mean, you kind of do feel smarter when you write it down like this. I mean, at least I do. Even though, like, I don't understand it. Let's see, cosine and sine in Fourier series can be thought of as an orthogonal basis where the scalar product is given by the integral. Okay. Yes, I'm reading the Burn report paper right now. That's the missing part of my master thesis. Oh, okay. Best of luck with that, my friend. Once it's published and once you present it, I'm pretty sure you're gonna be able to like earn your master's soon. I wish you the best of luck with the research, with that part of the research. But I'm pretty sure you'll get it done. Sasha, you're one awesome smart person. At least in my book, you are. Let's see. Okay, which completes the construction of the full Fourier series. The numbers is given by the Fourier series. L1, where the original function f is defined and may be divergent, or maybe have a different sum than f of x. Okay. Let's see. A function f is said to be piecewise continuous on an interval a and b if it is continuous at all, but infinitely many points in a and b where it has jump discontinuities. That is, at any discontinuity point x, the function has distinct right-hand side and left-hand side. Finite limits. Okay. If f is differentiable from both and both f and f prime are continuous on A to B, then f is called smooth on A and B. If at least one of f prime is piecewise continuous on A and B, then f is said to be piecewise smooth on A and B. Huh. And I know in multivariable calculus you learn about curvature, or at least you learn about the abstract definition of curvature, which I don't remember. Let's see. Figure 2.3. Where is that? Or unless it's talking about the definition. Here we go. Figure 2.3. Oh, it's underneath. Okay. It's a piecewise smooth. It's piecewise smooth, and the one on the right is not. Since f of 0 does not exist. Oh, okay. The graph indicates that the function increases without bound as the variable approaches the origin from the left. If f is a piecewise continuous on negative L to L, then the values of f at its point of discontinuity do not affect the construction of its Fourier series. More precisely, the integral from negative L to L f of x dx exists for such a function and is independent of the values assigned to it at its finite many discontinuity points. So the limit kind of wouldn't exist in this case. I mean, that's the way I see it, but I'm probably like mistaken here. Unless it just basically says it converges to 0 on both sides. Well, not converge, I mean like basically the limit is at 0. That's what I meant to say, from both left and right side. But piecewise smooth and piecewise, what was the other one? Piecewise continuous. Is it because like it's just touching the y-axis? That's why it's considered like, I guess, piecewise continuous? I mean, that's how it looks to me, but I don't know if that's the right way to actually phrase it. Let's see, theorem. If f is piecewise smooth on negative L to L, then its full Fourier series converges piecewise to the periodic extension of f to R at all points x where this extension is continuous. Let's see, half at the points x where the periodic extension of f is a finite discontinuity jump. This means that at each x in L, negative L to L, where f is continuous, the sum of the series is equal to f of x. Also, if the function f is continuous on negative L to L, such that negative L is equal to f of L, then the sum is equal to f of x at all points x in negative L to L. Okay, well, we're given an example here. Let's see, the periodic extension is both interesting, but at the same time, it's like I feel as if like my idea of what it means to be continuous and smooth is like totally like changed, because it just looks like it's a triangle that's just hugging the y-axis, and I end up wondering, it's like, I guess like when I think of continuous I think of like curves, but now these are just like straight triangles. So x plus 4 is equal to f of x for all x in using okay, so we're actually given examples now. Yields the Fourier series by the theorem of, where is it, 2.5. Oops, went too far. X is equal to 0 when it's 1, and that is the series converges to f of x for 2. So negative 2 is less than or equal to x, and x is less than 0. And 0 is greater than x, and less than or equal to 2. Where the periodic extension of f is continuous at point 0, whereas the extension drops discontinuously and the series converges. The graph function define the sum. So from here and here, so this one is let's see, x plus 2. To construct the full Fourier series of a given function f. In each case, use the appropriate sketches and discuss the convergence of the series on the interval L minus L to L, where f is defined. So, okay, oh cool, we have a lot of problems here. I'm still kind of confused on how this works. Keep the good work. Or I'm guessing you mean keep up the good work. Is that what you meant, Sascha? I feel like I'm gonna have to look more into this. well, that will do it for today's study session. Yeah, like, I think, like, the thing that's, like, really interesting is that, we learned what, piecewise continuous is, which is, like, this, and I'm like, oh, that's what it means? It looks like just, like, a triangle, just basically trying to form another triangle on the other side of the axis. And piecewise smooth, that's something I never thought I would, like, learn. But I do like the way that the Fourier series is, like, in its full form. It looks pretty cool. I mean, it looks like, it might look like a mess to somebody who doesn't know it, but at the same time, it just looks really, it looks really pretty. Like, people would probably look at it as like, what is that supposed to mean? I mean, I think it looks brilliant, but, you know, you guys be the judge. Oh, probably should have it down here, because chat is blocking it. I think, like, what I like is that when they break every part down and you can just basically rewrite it into its full form. I think that's, like, pretty cool. But then again, like, if you have the equation that basically talks about everything within the standard model of quantum mechanics, that's a real mess. I mean, for me, like, I don't, like, for me, I think it looks pretty cool because it looks like ancient hieroglyphs, but at the same time, it's like, I think everybody would be afraid of solving that equation. I mean, solving for this is also pretty scary too, because, like, if you had to solve for, like, x for the whole thing, that would probably be, like, kind of, like, intimidating to do, because there's, like, so many symbols in it and so much manipulation you have to do. Okay. Well, that will do it for today's study session, guys. Hopefully you guys enjoyed our little escapades. So we'll be back next week. And also, big apologies for yesterday, because I actually had to help my dad with certain things, and I realized that, like, I was late, so that's why I basically didn't stream yesterday. But we managed to stream today, and we managed to get a couple of stuff done. So we didn't learn a bit about Fourier series, but I probably have to continue studying a little bit more on those. And special thanks to all of the new people that followed on Twitch, in addition to some of the people that basically posted some problems up. So for my friends in Twitch chat, if you guys are lurking, thank you for lurking. But if you like math, physics, or just a study stream to keep yourself productive on any projects you're doing, be sure to give my channel a follow if you can. And also, I will provide a link to our Discord server for those on Twitch, in addition to my YouTube channel if you want to catch up with my previous VODs, I mean. In addition, I'll also be streaming on my video game channel, so my Uncle Talks channel, if you also want to follow me there. I basically just talk to you guys while I play video games there. And for all those that are watching on YouTube, everything is in the description down below. If you want to check out all those links to my basically my Twitch channel, as well as my Discord server, as well as my Uncle Talks Twitch channel. So I feel like we should do a raid today, because we haven't done a raid in so long. Let's see if there's anyone on. Let's see if there's anyone on that we can raid, so that way we can keep the knowledge going. Let's see if there's anyone doing math. want to do a raid, we can't raid into anybody. Unless anyone in chat has any suggestions on who we should raid. And if not, then I'll just probably end it here. Let's try maybe science and technology. Let's see if there's anyone streaming that type of content. Yeah, I don't see anyone that we can probably check out. Oh well, I guess we'll just end it here. So, thank you for joining me today, guys. And always remember, everyone is precious. You guys are just as precious as everyone else. And I will see you guys in the next stream. And if you're checking this out on YouTube, I will see you in the next video. So take care, guys. Bye-bye.